Welcome back to the EXD. Last week we took a deeper look at inference benchmarking with Llama-benchy. For example, we learned about how overall token generation can speed up under concurrent loads. This week we look at speculative decoding, aka multi-token prediction or MTP. Speculative decoding is a rather clever way of better utilizing your compute resources in the decode pass. Today we'll just show you that it actually does work, and in a future episode when we introduce LLM architectures we can understand why it works. My name is Ram and I work at the Ethereum Foundation on AI Ops, and this is an open learning log for what I call the EXD. Check out episode 1 to understand what the EXD is all about. I'll link it in the description below. Okay, let's start. What is speculative decoding? The idea is actually pretty simple. A smaller model proposes and the big model verifies. So the idea is, if we have a single large model which is predicting tokens one by one, the compute pass is quite expensive. And this is true even for what you could imagine are throwaway tokens like at or the or simple conjunctions or otherwise, let's say, more obvious tokens that maybe a smaller model could guess at. And so the idea is, why not get a small model to make guesses at the next tokens, maybe 2 or 3 of them, and then a big model can just verify those tokens in one go. This is a little confusing, so let's take a look at a visual simulator to kind of get a sense of this. So this is sort of one of our visualization consoles for LLM inference. You basically have the draft model over here, and you have a full model over here. And the idea is that the draft model guesses 2 tokens, and this will happen in 2 passes. It'll guess 1 token, and then based on that first guess, it'll guess the second token. And then it'll hand it over to the full model. And it turns out that due to some details of the architecture of transformers, etc., the model can actually verify both of these tokens in just 1 pass. So this is basically how this setup works. The draft model, being much smaller, can actually guess the 2 tokens very quickly. And the full model just does a single verification. Okay, so let's look at an example. The quick brown fox jumps over the lazy dog. This is a well-known mnemonic. So in the next step, the draft model makes its guesses, and it says, I'm guessing fox and jumps. Then it hands this over to the full model, the big model, which in 1 pass says, yeah, I like these answers, let's keep them. And so then we go back to the draft model in the next step, and it guesses over, and let's assume it makes a mistake here. It says some nonsensical thing. And remember, this happens, first it guesses over, and then it sends the whole sequence again and guesses this next thing which is wrong. But because it's a draft model, that's much quicker than having the big model do it. Once again, in the next pass, the full model verifies it, and it says the first one looks okay, but the second one looks wrong, it should be and it does the correction in 1 pass. And then we go to the next pass, and similarly, it guesses lazy and dog, and the full model verifies it in 1 pass. So this is basically sort of the setup. You can do 3 tokens. So for example, you have the quick brown, and this time the draft model will guess 3 tokens. So it'll go the quick brown fox, it'll make that first guess, then it'll loop through these again, and then guess jumps, and then over. And these 3 will then be verified in 1 single pass by the large model, and says, yeah, that looks right. Fox jumps over, looks good. Moves forward again, and let's assume here it makes a mistake. So it first goes and then runs all of this, and instead of the lazy dog, maybe it says the active dog or something. So it goes through 3 quick iterations because it's a smaller model. Then once again, it hands it over to in the next step to the full model, which then verifies it in one pass and says, hey, it's not the active dog, it's the lazy dog. Makes the correction in one pass, and the sequence is complete. So that's pretty much the picture of how speculative decoding works. It's quite clever. The idea is you don't need to really apply the same amount of intelligence for every single token. Maybe some tokens can be generated by a small model, and more complex or tougher conceptual tokens can be handled by the larger model in a verification pass. Let's see this in action. So we're back in VS Code. If you remember, I run my benchmarks from Yoneda, and these run against the AI top atom over here, and we're already inside the project serve folder from where we can run all our commands to bring up models and take them down, etc. So Yoneda is where we run the benchmarks, and this is where we have our AI server, and we can change the models that are running, etc. Already. So let's do a quick benchmark setup. This is exactly the same as last episodes. We first export some common arguments. So we're saying this is the base URL. Let's test it against this model, and let's run that. Okay. So we're ready to run a benchmark. And on the AI top atom, let's first run this without any speculative decoding. So let's just look at what that looks like. So if you remember, our configs are stored inside the configs directory. So this is the multi-token prediction 0 config, and this is what it looks like. Familiar arguments here. This is the model name, memory utilization, etc. There's a whole bunch of VLM args which we will slowly understand one by one. But the main thing to notice here is that there is no speculative decoding mentioned, which we'll see in subsequent benchmarks. Okay, so this is the config that we're going to run. So let's get that up and running. This is my little utility command to run this particular config. This will, of course, take a couple of seconds, so I will meet you guys when it's loaded. Okay, we're back. The server has started, and let's run our first benchmark. Remember, we're running this benchmark against a model with no, a VLLM container with no speculative decoding. So this is what we're going to run. If you remember, this basically runs a prompt with a prefill length of 512 with a target output size of 256, and we're just going to do a single user run because these things take time, but we're going to do 3 runs so that we can average across those 3 runs to get a good sense of whether or not speculative decoding will make a difference in subsequent runs. So let's run that. This should hopefully run kind of quickly. Let me, in fact, meet you guys when the run is complete. Okay, looks like run 1 and 2 have completed, and run 3 is just about getting done. And any moment now we'll have our results. Okay, so these results have been saved to this file, quen35bmtp0. Single. So let's just see what that looks like. I have a little convenience script here that just summarizes what we got, and essentially these are the two numbers we want to kind of focus on. This was the prefill speed. If you remember, this is not really affected by speculative decoding because it just tries to speed up the decode loop. It's really this, the token generations per second. So right now we're sitting at 30.4 without any speculative decoding. So the question is, what happens if we do speculative decoding? So just to remind ourselves, this was the let's see where is it? This was the config we just ran. Oh, no wonder, I'm in the wrong machine. I should be looking at that here. This is what we just ran the benchmark against without speculative decoding. And what we want to do is run it against MTP2. So basically producing two tokens ahead of time. So the only difference between these two, let me just make it a little smaller so you can see both, is that this has got this extra flag now. This was the one we're running right now. This is the one I'm going to run, and it has a speculative decoding config, and it says the number of speculative tokens should be 2. Okay, so let's pull down the previous server and let's get the new server running. So we're pulling down the one that was running, and we are now setting it up. We are now running the default mode, which has the number of speculative tokens set to 2. I'll start this up and meet you guys when the model is loaded. Okay, the model has loaded again, and this is now the default model running a speculative decoding of 2 tokens. Let's run the same benchmark against it and see how this one does. Once again, while it's running, running it in the wrong place. I should run this on Yoneda. So there you go. So once again, the prefill is 512 bytes long and the target is 256 tokens output, and we're going to do 3 runs. So I'll meet you guys back here once the run's complete. Okay, so the run is completed. Let's see how this did. So actually before that, let's remind ourselves. This is the original run with no speculative decoding, and we got token generation of 30 tokens per second. Let's run the MTP2 benchmark and see if we did any better. Looks like we did much better. So under this run, exact same kind of benchmark, we seem to have moved up to 46 tokens per second. So what if we bump it one more time? Let's push it up to speculative decoding of 3 tokens in one pass. So as you can see here, the number of speculative tokens is 3. And let's see if this makes a difference. This is obviously going to take a second to load, so I'll meet you guys back once it's ready. Okay, our new model is running. It's aggressively, speculatively proposing 3 tokens every inference pass. Let's see how it does. So let's get back to Yoneda and let's run the benchmark. Okay, this is going to take a minute. Let me pause and catch up with you when it's ready. And we're back. the benchmark completed. Let's see how we did. So if you remember, the first run was 30 tokens per second. The second run was 46. And here we seem to have regressed a little bit. We're back down to 42.9. So just for a quick comparison, the first comparison is between MTP0 versus MTP2. We ended up with a 15% speed up in token generation. But if you look at MTP2 versus MTP3, we actually lost some speed. Okay, so basically this tells us that you can't just keep extending your speculation as far as you want. Obviously, at some point, you're going to be discarding more tokens than the ones that are succeeding, at which point you're basically losing speed. And it looks like these benchmarks seem to suggest that maybe 2 is sort of the optimal number of tokens to predict for this setup, though we can dig into this further in future episodes. But yeah, I think this is a good place to stop. I've been noticing that my episodes are getting longer and longer. So what we did in this episode is we looked at speculative decoding, a very clever technique of using a small model to kind of guess all the more obvious tokens and leave sort of the more valuable tokens for a bigger model to guess, and thereby improve the performance of our LLM models. This also kind of, I think, marks the end of maybe a first phase of the EXD, where we took a cutting edge model and we ran it and just kind of looked at the inference performance. And this is kind of the philosophy of the EXD, right? We want to start with something that's already, fully performant and state of the art, and then slowly uncover that layer by layer. And we have sort of taken off the first layer and just looked at the broad internals. We understood the 2 phases of an inference pass, prefill and decode, and then we introduced some ideas like speculative decoding to speed up this process. And this is kind of like a standard inference setup in today's LLM world. So maybe next week in episode 6, it would be a good opportunity to actually take stock and think about what to do next. See you guys then.